Okay, this problem, you have given a grid. This grid consists of these cross marks or walls. The star is where you are currently positioned. A square symbol that represents some keys. You have three keys, and you have rings. Rings represents log. So you have three logs, corresponding logs. The problem is you have to travel across the and connect all the keys. You need not open the lock, but you have to connect all the keys. You have to this one, this one, this one. So, and the issue is without having key, you cannot pass through point. Lock is there. So, without having key of 3, you cannot cross this way. You cannot come into this way. So, if you are coming from here to here, you will be connecting only the key number 1. So if you directly reach at bottom, you will be blocked because you don't have key number 3. That's a problem. But if you are going through number 1, then going to number 3, then returning back and coming down, then you will have key number 3. At same time, you have a key number 1 as well, so you can go to the left portion as opening this lock as well, and you can connect key number 2 as that will be having all the keys given in the. So the question is you need to return the minimum number of steps you have to do so that you will be having all the keys with you. So how do you go with this problem is a primary thing. This star is I used symbolically in the problem. It is at the right. This walls are represented by some hash symbols. The keys will be some lowercase letter. For every lowercase letter, there will be a corresponding uppercase letter which represents the corresponding lock. It is not possible for you to always collect all the keys. So if it is not possible to collect all the keys, you can simply return -1. Otherwise, you have to return a number which represents a number of minimal steps you have to take to collect all the keys. That's a problem. Hope you got the problem statement. This is a kind of breadth first search. It's a kind of multi-layer breadth first search because see, this when you reach here, you can have two situations. Either you have key number 1 or you have key number 1 and 3. These two has to be addressed separate. Then only you can decide whether these two situations are different. It is not a simple breadth first search. So you have to handle both situations separately on a different domain altogether, different plane of domain altogether. So how do you code this? And once you go through the code, you will get more clarity how this plane has dissected and bifurcated into multi-plane in a way you can address this scenario, having one key and having two keys. How we will do that? We will see at the. So this is the sample test case given. Same as what I had shown just, but it has only two keys, a small m and a capital M, and there is a key B and a log capital B. These hashes are one, and you will be initially you will be placed at the position where the @ symbol has depicted. So let's start. You have to. It's a breadth first search. We're definitely having some queue. So you have the queue. Now you wanted to take queue your initial position. From there on, you will be starting the breadth first search. Because let's take the parameters, size parameters of it. And you have to go through the grid and understand where this act is there and how many keys are there. Based on that, you can plan your future and how you will proceed with this problem. So I plus okay. Now if the grid of ij equal to, that is the starting position, exploration starting position, breadth first starting position. So you have to give that point. And you have to mark it as visited as. And when you mark it as visited, you will be having, as I said, you will be having at max six keys. These 6 keys can be represented using bit representation. Will be requiring six bits to represent 1, 2, 3, 4, 5, 6. 6 bits to represent all these things. So you have 6 bits, it will account to the number 64. This will be 64, this will be 32, this will be 60, this will become 8, 4, okay. Okay, this is not 60. Just 30. It will be 16, 8, 4, 1. So in total, if you add all this, it will give you 60. 60. So you need a space for visited array. You are defining visited array. 3-dimensional vector. Till horrific. Though it's not. It's unusual to solve a lot of problems to have a 3-dimensional vector. It's a visit em spaces. M rows and columns. 64, 6 space to represent the number of keys you are possessing when you reach at some point. So when you start, you have no keys. So you can simply keep it as 0. That is the one thing you have to figure it out. The next thing is you have to understand your maximal number of keys. Initially set as 0. It's a grade of ij. If it is a lower, then maximum number of keys will be like the maximal lowercase letter you will be getting when you do the operations. When you scan this grid. So ij, if it is a small letter, you will have to take the difference from the small letter a. This you can get what is the maximal number of keys which is there in the system, in the grid. Now you have to do this. Breadth first search. Q.empty. This is the outer layer of breadth first search. You will be dequeuing the content of the front of the queue. X B Q dot 0. Does it work? Does it? It is not work. Take C. You receive X and Y coordinates of your front of the queue and remove that element from the queue. Now you have to explore it Before that, it's not only just coordinates. You have to keep the representation of keys as keys you have is like q dot dot. If this key, if this key is, if this key coordinate represent all the keys you have max 4 keys. So when you do that, when you convert that into kind of binary representation, you will have one left shift max number of keys minus one as your key representation. If you have all the keys. In this case, you can simply represent, you need that layering. This is the space you need layering. It represents the number of steps you have from your initial exploration point. You keep it at 0 initial. Now you take the size of your queue. While this size does not falls down, while the size does not hit 0, that means while the time you conclude your current exploration, you are at layer 1, you will be exploring your layer 1 and you will be identifying a lot of layer 2 elements. So, it may not be layer 1, it is layer 0. We put it as layer 0. So you have to explore all the layer 1 elements, layer 0 elements at a stretch. Then you go for layer 1 elements at a stretch. Because all the layer 1 elements, you don't need any step movements. For all the layer 2 elements, you need one step movement. That's why you are exploring all the elements in a layer at a time. So when you're exploring elements in a layer at a time, you have to pop out the element first, and you have to check whether it satisfies the condition that you collected all the keys. If not, continue to explore its networks. You have to enqueue them for next exploration. So how do you do that? You have travel into all 4 direction to check all 4 direction. Minus. This is some representation which can help you to rotate over 4 neighbors of your current. So I then 4 pi plus plus. I will use k and l as coordinate of your neighbor. So it will be like k x plus ti I will be your x coordinate of your neighbor. L y plus ti I plus will be the y coordinate of L will be the y coordinate of your neighbor. This dir helps find your neighbor in all 4 directions. By the time this loop travels from 0 to 4, 0 to 3, you must have explored whole. Now let's check. Now we need few conditions. Whether has this coordinates outbounded the grid or not. If it has outbounded, we'll be checking. We will not be exploring those coordinates. Or the first 4 criteria are to check the boundary conditions of the grid. The 5th condition is to check whether it is a wall or not. If it is a wall, we go in that direction. If it is a wall, we cannot move in that direction. In all these conditions, continue. Otherwise, what we can do is like you have few more problems. Suppose if it is uppercase character, if is upper, instead of k and you don't have the key for to open that lock. Uppercase means it's a lock. So, and you don't have the key. You don't have the key. E this feel like J is unmet and different. If it is a lower one, how to get a copy of, because you have to get a copy of it because you require this for next iteration of IS. So it is a it's a lowercase letter. You have new key with you. You have to append that with your current key. Yeah, you appended that with your current key. Basically, you added that into your key list. Now you have to mark that as visited. K visited and enqueue this location with its key set for further exploration. That this concludes the problem because you you started exploring the you started exploring the grid from your initial point layer by layer. When you found a key, you added that into your key list. You enqueued that for further exploration. And if somehow it reaches at a point where you have all the keys, then we're returning that as your answer. So this is the solution looking for. Let's test and see whether this test case works or not. This shall give 1, 2, 3, 4, 5, 6, 7, 8 moments. Mostly. If it is giving a 8, some it is giving. That's bit better. Think what went wrong. Only one did input recorded. both. Okay. Still. Second test. Even that is a problem. Nice. Okay. We have checked the condition of the visited. Case. So problem visited. See the reference here. Take down product, because if it is up to the key, should I make it? Test, test. There was a small error. We kept greater than or equal. And it took so much time to debug that. We made a mistake over here as well. It was uppercase letter, and we chose the lowercase letter. This is the problem of live coding. Hope you understood from the solution. The landed. It will be like 1, 2, 3, 4, 5, 6, 7, 8. Thanks for listening.